Okay, so Organic Chemistry 2, summer 2021. This is our schedule. We're going to have an 8-week semester, so class wraps up around July 8th. And if you're wondering, what are we going to do on which days and when will the homework be due and when will quizzes be due? Well, now you know because everything is outlined on this schedule. Keep in mind this is a flexible schedule. It might change as a function of the rate at which we cover material. Our class will be on Microsoft Teams on Monday, Wednesday, and Thursday from 1 to 4:30 p.m. And you can see, for example, today we're going to be looking at Chapter 11, which deals with synthesis. And you have Quiz 11, which is going to be on Thursday, and Homework 11. It's also due that day. After that, we're going to tackle Chapter 12, which deals with alcohols and phenols. And you can see that the quiz for that is on Monday, as is the homework due date. So all the due dates are outlined on here, and then towards the end of the semester, the summer semester, we have a couple of days allotted for review, and then the final exam will be on July 8th, and that'll be all she wrote, so to speak. Anyhow, I wanted to take a brief moment to take a look at the syllabus for this class this summer. So if any of you haven't had me as an instructor before, and I know there are several people who haven't, my name is Mr. Dion, and traditionally, Organic Chemistry 2 has been taught at UCCS as a face-to-face course, but on account of the pandemic, we are going to do the class online this summer. Again, the lectures will be on Monday, Wednesday, and Thursday from 1 to 4:30, and it begins today and ends on July 8th. I do my best to record the lecture videos and post them to my YouTube channel. I don't promise that I will do that, but I do my best to do that. And again, the reason why I only promised or to do my best to do that is because this is a synchronous course. Okay, so we have lecture times for you to show up. Things that you need to complete this class: you need to have a reliable internet connection in order for attending and participating in live lectures. And if I post any pre-recorded content, you'll want to be able to watch that. You also need a computer with a webcam and microphone so that you can operate Respondus Lockdown Browser and Respondus Monitor during our quizzes and exams. And Respondus Lockdown Browser and Respondus Monitor are merely a program that is used to mitigate cheating amongst students. You also need a printer for a couple of assignments this summer, and the reason why is because I might get you to, or I probably get you to do a few things by hand, and then you need a way to scan those in, and you do not need a fancy scanner to scan anything. I'm an instructor and I don't own a scanner, but I do have a smartphone, and with that, you can download any one of, Avogadro's number of free apps that are available for scanning, and converting to PDF. Anyhow, what do you learn in Organic Chemistry 2? Well, you'll learn a whole lot about synthesis and mechanisms and reactions in this class. In order to enter into Organic Chemistry 1, or Organic Chemistry 2, rather, you need to have passed Organic Chemistry 1 with a grade of C or better. How many hours a week will a student spend studying for Organic Chemistry 2? I'd say that varies from student to student, but generally somewhere between 12 and 18 hours a week will probably do the trick. Some students might need a little less, some students might need a lot more. Again, it depends on the person. Keep in mind that quizzes are inherently cumulative, so what you learn on one chapter could be quizzed on the next chapter. If we learn something in chapter 13, I can ask you about that 2 weeks, 3 weeks, 4 weeks later. Everything is fair game in this course. If you want to reach me, the best way to do that is to contact me by email. My email address is right here. Don't use the messaging feature on Canvas. Write to me using your university email. Do not write to me from a Hotmail or a Gmail account. And if you need to speak with me, just let me know and we'll try to organize a time where we could chat together on Microsoft Teams. Again, use your campus email when contacting me. Do not use personal email accounts. Here's a little blurb about some course outcomes, some things that you'll learn throughout the semester. We're going to talk more about infrared spectroscopy, NMR spectroscopy, mass spectrometry. We'll talk a lot about multi-step synthesis in this class. In fact, that takes up most of our time. And towards the end of the course, we'll talk a little bit about biochemistry, like carbohydrates and amino acid proteins, so on and so forth. Our textbook is Organic Chemistry, the 3rd edition. The author is David Klein. It is published by Wiley. Um, I suppose you could go to the bookstore at UCCS and buy a hard copy of the book, or you could find one online. If you find a 2nd edition, that will work totally well. There's no problem with that. However, everybody who's hearing the sound of my voice has access, complete access, to the electronic textbook, and I'll show you how to access that in a little bit. You also have complete access to the solutions manual, not an answers guide, a solutions manual, which is very well done. Everything in this class is done on Canvas. I have all of the links to your quizzes, your homework, your grades, slides, anything else that I post will be posted to Canvas. Here's our approximate grade scale here. So your quizzes are worth 70% of your score. The final exam is worth 20%. Your homework is worth 10%. The final exam will be an ACS final or similar exam written by myself, and you have to complete the final exam in order to pass the class. Now, a little bit more about your grade. There is no extra credit in Organic Chemistry 2. There's no, coming to me at the end of class and saying, I'll make a poster and then I'll get a good grade. No, you have to complete everything during the class. The homework scores, again, are weighted to 10% of your grade. If you want to submit a homework assignment late, there's no problem with that at all. However, the maximum score that you can get is 50% of the available points. So let's say you submit a homework assignment 2 days late, or an hour late, the maximum score you could get would be 50%. Okay. No makeup quizzes will be given. If you know in advance that you're going to miss a quiz for some reason, let me know and we'll try to work around that. And I can't promise that I'll do that, or that we can, but I'll try. If you miss a quiz, you will receive a score of 0. I don't care what the reason is. If it was, as mean as it might sound, if it was a death in the family, or you got in a car accident, or your cousin, fell off a building, or, your grandparents died, whatever. You will receive a score of 0 for any quiz that is not completed. So in order for me to drop your lowest quiz score, you have to write 13 quizzes. So if you write 12 quizzes, for example, let's say you miss one, I will not drop your lowest score. Okay, if you miss 2 quizzes, well, then one of them will count as the dropped one of them will count as a 0. Okay, so you have to write 13 quizzes in order to have 1 quiz score dropped. As far as grading goes, most of our quizzes will be electronically administered, and so they'll be graded very quickly. But if not, I usually try to get the grading done within a week. Academic honesty, cheating will not be tolerated in this classroom. So make sure that any work that you do is your own. And I'm going to talk more about the etiquette for Respondus Lockdown Browser and Respondus Monitor later on in the class when we get closer to our first quiz day. In terms of online classroom courtesy in the online classroom, or proper netiquette is what they call it, is if you have any questions, feel free to unmute your mic and just politely ask me what you want to know. Or you can also type things in the chat, and I keep an eye on the chat usually while I'm lecturing. I do my best to keep an eye on that if you have a question that you want to put in there. Our census date is May 24th. I neglected to point that out. It is highlighted on the schedule. So that is the drop date. You have 1 week, and so you get a little bit of feedback before then. Towards the end of the syllabus, I have some information about withdrawing from the lecture, and you can go ahead and read that. Some other information about course evaluation. Something that I'm not sure about is the Science Center summer hours. I'm going to have to look into that to see if it's even open. I thought it was, but I'm not 100% sure. I have to talk to Dr. Phillips about that to get some more information. If you have a disability and have an accommodation for that, please contact me as soon as possible regarding that accommodation, and I will take a look at it. And there's a little blurb down here at the bottom for military students, so make sure to read that if you are in the military. And of course, information in the syllabus is subject to change depending on how things go throughout the summer semester. So that's a little bit about our syllabus. Now I wanted to take some time to take a look at our class's shell on Canvas. So this is my Canvas homepage. I'm sure yours doesn't look exactly like this, but if you open up our course on Canvas, it should look something like this. If I go into student view, this is exactly what you should see when you log into Canvas. You can see there's a getting started module. There's a link to the syllabus and schedule. I recommend printing at least a couple of copies of the schedule and putting them, in important places so you always know what is due when, you know what we're covering at lecture, in such and such a date. You see there's a link for the textbook, and I'll talk more about that in a second. And then below that, you'll see that for every chapter, I have a module where I have the lecture slides posted as PowerPoint files that you can take and print and convert them to PDFs, print them any way you want. So I have those. I also have suggested practice problems. Say, for example, we're doing chapter 12. You'll see there's lecture notes. Then if you open up this suggested problems, what I've done is I've gone through the textbook and I've handpicked the problems that I think would be the best ones for you to tackle, because there might be some questions in there that might not be pertinent to Chemistry 3111. Maybe there's something in there that we skipped. And so I've saved you the hassle of having to wade through which problems are most important. Then if you keep moving beyond there, beyond all the chapters, you'll see that I have the links for the online homework, chapters 11 all the way through 27. And you can see there's a couple of chapters in there that we don't complete, but all the online homework, I believe I set it up so it's all ready to go. So if you wanted to start the chapter 11 homework today, feel free to do that. There's no problem with that whatsoever. So I also want to show you another thing before we leave Canvas. I'm just leaving student view because otherwise I won't be able to do it since I'm an instructor. But you see where it says textbook and then it says Wiley Plus Read, Study, and Practice. If we click on that, that opens up this tab, and we click on that, it should open up a link to our textbook. Now you can read the textbook from this page, and you see you have chapters 1 or sections 1 through 1.3. If I move ahead to chapter 11, which is what we're looking at, right? You see all the links to synthesis and all that. That's great, and you can read the textbook there. I recommend clicking on the link at the top left that says downloadable e-textbook, which takes you to an actual electronic version of our textbook. So it's opening up right now. We'll give it a second. But let's say, chapter 11, you can see you can start reading here and plow your way through the entire chapter, reading here. Every bit of information is in here. Not only do we have practice problems in here, let's say I assign question 11.3. If you want to see the solutions, not just the answers, but the solutions to these problems, you would click on the 11.3. So I clicked on it. We'll give it a second. And it opens up a solutions manual, not just the answers, but solutions to these problems. So the solutions to almost every problem in the book are worked out in here. And you can see not only do they have just the chemistry, but there's also text involved in here. And sometimes students will ask me, hey, Mr. Dion, is there a summary somewhere? Or is there a review? Well, in the solutions manual, there's reviews of concepts, reviews of skills that you can practice, all kinds of different things in there that you could take a look at to help guide you through the class. Okay, so again, the downloadable e-textbook, and then you have access to the full text as well as a beautiful, beautiful solutions manual. So the book is really your Bible, in this class. It will help you out a lot. Okay, there we go. So that's our class's Canvas page. And again, this is what mine looks like. If we go back to student view, this is what yours will look like. And you can see there's a grades tab there. And I also post announcements. You can just see that I posted an announcement today. The class begins at 1 p.m. That was just a gentle reminder for anybody who might have missed that. Anyhow, there you have it. Well, let's go back to Microsoft Teams and just open this up here and ask my students, are there any questions? Does anybody have any burning questions about the syllabus and schedule?
I have a question about the textbook.
Go ahead.
Does the textbook we have from the fall carry over into this semester?
It's the exact same textbook, Klein 3rd edition. Yep. Identical textbook. There is a new edition that's coming out in the fall, which will be the 4th edition. However, I won't be adopting the 4th edition until January 2022. So last semester's textbook is the same one as this semester. Any other questions? Okay, well, if there's no questions, the first chapter will be a review for my students who are in Chemistry 3101 with me and who just finished the course. we finished that, just a little more than a week ago. And so we begin in Chemistry 3111 with Chapter 11, which deals with synthesis, which again is the last chapter that my former 3101 students did. And the reason that we do that is for anybody who's taking this class who hasn't taken Organic Chemistry 1 for a while. It will be a good review for those students and really help them out in remembering all of the reactions that they would have learned in Organic Chemistry 1. So again, it's going to be a real hardcore review for some students who would have just covered this content with me maybe like 3 weeks ago or something. But again, for students who haven't taken Organic Chemistry in a while, and of course, we love to have those kind of students in the classroom, it'll be a pretty useful review for you. Okay, well, if there's no further questions, I'm going to try to find my slides here, and then we'll talk about synthesis, which is Chapter 11. So let me get set up here. And again, you'll have to forgive me. I had a 3.5-hour class this morning. I'm still kind of getting my lecturing voice back, so I might take a little more breaks than usual today, depending on how things go, but we'll give it the old college try. All right, so Organic Chemistry 2, Chemistry 3111. This is Chapter 11, which deals with synthesis. Again, if you took Chemistry 3101 with me recently, this will be a review for you. However, if you have not taken Organic Chemistry for the last semester or maybe a couple semesters ago, this will be a really handy review for you. And the way that this chapter begins is just by talking about what are called one-step syntheses, or in other words, just a reaction, that we've looked at, or a one-step, sort of transformation. For example, let's say you wanted to take this molecule here. This is isobutylene, and you want to convert that into this dibromo alkane. Well, how would you do that? Well, you're going to have to treat that with bromine, right? You'd have to treat that with Br2. It proceeds through a bromonium ion intermediate. You could even write down a solvent here if you wanted to, maybe carbon tetrachloride, which is a, inert solvent, won't react with the bromine. And so you need to know all the reactions that you would have, learned in chapters 7 and 8 and 9 in Organic Chemistry 1 if you did that class using our class's textbook, so Klein 3rd edition. And so let's take a look at questions 11.1 and 11.2 before we really get into the nuts and bolts of synthesis and looking at multi-step synthesis. This is question 11.1. It says identify reagents that you could use to accomplish all the transformations below. If you're having trouble, these reagents, or the reagents, for these transformations appear in the review of the reactions at the end of chapter 8, but try to do it yourself without help. So if you, again, haven't taken organic chemistry in a while, chapter 8 deals with the chemistry of alkenes. So this is alkene chemistry. Okay, and all the reactions would be covered in chapter 8. So again, this chapter is nothing more than a review. All right, well, let's say we have this molecule here. This is 1-methylcyclohexene. We want to take this guy and we want to convert it to this molecule where we have a bromine and a methyl. So this would be what? 1-bromo, 2-methylcyclohexane. So I want to ask my students, does anybody know, would this be a Markovnikov or an anti-Markovnikov? Be a Markovnikov or an anti-Markovnikov addition of HBr. You can either unmute your mic or you can type the answer into the chat. Would this be Markovnikov or anti-Markovnikov addition? Does anybody have an idea?
It's Markovnikov, right?
No, it's anti-Markovnikov, right? Because Markovnikov is when the rich get richer, right? That's the rule we use there. So if we look at the double bond, you see that in the double bond, we have a hydrogen here, and we have no hydrogens attached to this carbon. So if the bromine is being added to the carbon that already has a hydrogen attached to it, this is in fact an anti-Markovnikov addition. So we'll type that, or we'll write that here, anti-Markovnikov addition of HBr, right? And how do we do that? We use HBr and peroxides, and that's something that we covered in chapter 10. We looked at the mechanism for that. All right, if we want to do a Markovnikov addition of HBr, which is what's happening here in this reaction, this is a Markovnikov addition of HBr, right? You remember the rule for Markovnikov addition. The rich carbon is the one that's getting richer, right? Because we have two hydrogens over here now. And so in order to effect a Markovnikov addition of HBr across that double bond, we simply use HBr, right? We just use hydrogen bromide or hydrobromic acid, and you should be able to draw the mechanism of that reaction as well. Well, let's keep going here in a clockwise fashion. We take this alkene, again, our 1-methylcyclohexene, and we want to make this bifunctional compound where we have a ketone and an aldehyde in the same molecule. Can anybody tell me what type of reaction this is? How you would name this reaction, or what one of the reagents might be? Yeah, this is an ozonolysis reaction, isn't it? Right? This is ozonolysis reaction. Ozonolysis of an alkene. The first step, yes, is to treat the molecule with ozone, and the second step is to treat it with DMS, which is dimethyl sulfide. Another option would be to treat it with zinc and water, but we're going to just stick with DMS and ozone since that seems to be most commonly used by the author of our textbook. Okay, so you could put here for step 2, you could put ore, zinc, and water. All right, so that's ozonolysis of an alkene. In this case, we end up with a methyl ketone and an aldehyde. The next reaction is this syn addition, right? It's a syn diol formation. So let me get a red pen out here. So we want to form a cis diol. So this is syn dihydroxylation. So that means that both hydroxyls are being added to the same face of the molecule. You can see that they end up being cis. They're on the same face of the molecule. And so the best way that we know to do that is to treat the molecule with a catalytic amount of osmium tetroxide and also put an N-methylmorpholine N-oxide, or NMO. And if you took Organic Chemistry 1 with me, you know that there's more than one way to do this reaction, isn't there? Right? We can use T-butyl hydroperoxide instead of NMO. We can use potassium permanganate in basic media. That will work as well. Okay. Next one is an anti-dihydroxylation. Right? We're taking that alkene and we're adding 2 hydroxyls, but this is called this anti-dihydroxylation. Just kind of abbreviate it there. Could anybody tell me what would be the best reagents to do an anti-dihydroxylation? Even an idea of how you might do an anti-dihydroxylation. If I could refer to some of my Organic Chemistry 1 students who would have studied this chapter, a few weeks ago. Does anybody remember how to do an anti-dihydroxylation? The first step is you treat this with a peroxy acid, RCO3H, like MCPBA. And then in the second step, we treat that with acid, aqueous acid. Okay. Next one is a halohydrin formation. So this is a halohydrin. How do we form a halohydrin? In the first step, I guess there's only one step really. We treat it with bromine, and then that reacts with the alkene to form a bromonium ion. But you do the reaction in water as your solvent. And water comes in and acts as a nucleophile. It attacks the more hindered carbon. And in Organic Chemistry 1, we talked about why that is, why it attacks the more hindered carbon. And you end up with an anti-addition of the hydroxyl and the bromine. And the hydroxyl, again, ends up at the more substituted carbon. Okay, next reaction is just a straightforward bromination reaction. In fact, that was the reaction that was on the last slide. A bromination, like that. Can anybody tell me how you would do a bromination reaction? How would I get from this alkene to this? Yeah, just treat it with bromine, absolutely. So Br2, and if you want to put a solvent in there, like, you know, CCl4, carbon tetrachloride, that works. And if you don't, if you want to just leave the solvent out, that's fine too. I think our textbook leaves it out most of the time. All right, next we have a hydrogenation reaction. Okay, so this is hydrogenation. And again, this is a very common reaction in Organic Chemistry 1 to take an alkene and convert it to an alkane. Thanks, Courtney. Yes, you would use hydrogen and palladium, platinum, or nickel. In this case, we'll use platinum. All right, so hydrogenation reaction. The next reaction, if I draw an arrow here like this, would this be a Markovnikov addition of water across the double bond or an anti-Markovnikov water across the double bond? It's one that I have highlighted by the green arrow. Is that Markovnikov or anti-Markovnikov? Yeah, so this is anti-Markovnikov addition of water. So this is one you really just kind of have to memorize the steps. The first step is borane, BH3, and THF. The second step is hydrogen peroxide and sodium hydroxide. That. The next one is a Markovnikov addition of water across the double bond. That one's a little simpler. Right, for that you just need H3O plus, just some dilute aqueous acid to do a Markovnikov addition. So we'll put Markovnikov addition of water. Remember that there are other conditions for Markovnikov addition of water. If you want to avoid carbocation rearrangements, you use oxymercuration demercuration, which is mercuric acetate in water followed by sodium borohydride. It's not on this slide, but that's still another important reaction. All right, I got a good one for you. What about this reaction right here? What if I want to take methyl cyclohexane and convert it to 1-bromo, 1-methyl cyclohexane? Could anybody tell me what I would do for a transformation like that? I want to take methyl cyclohexane and I want to brominate it. Just adding a bromine. There's only one way that we know how to react an alkane, right? This is an alkane. How do you treat an alkane, or what do you treat an alkane with to convert it into an alkyl halide, an alkyl bromide? That's covered in detail in chapter 10. So this is chapter 10, okay? And this is bromination. So we would treat it with bromine and light or heat, okay? It's a radical reaction, right? This is bromination of an alkane, okay? And the last reaction that we'll look at on this slide, so we want to take this alkyl bromide. Here is our alpha carbon. We have a beta carbon here that has 3 protons on it, and we also have this beta carbon here, which has these types of protons on it, right? So this is also a beta carbon. We're going to abstract the proton in red. So for that, we would need a non-hindered base like sodium methoxide so that it abstracts the proton in red, and we end up with the more substituted alkene or the Zaitsev alkene. If you wanted to make the Hoffman alkene, you could do that. I'll just kind of show you. If you were to take this and treat it with potassium T-butoxide, okay, in that case, you would end up abstracting the proton from the blue carbon, that beta proton, and you'd end up with this compound, which is called methylene cyclohexane, like that. All right, so there you go. There's a review of most of the reactions that were covered in chapter 8 or whatever textbook you studied Organic Chemistry 1 from. This is most of the reactions that you would need to know from your alkene chemistry days in Organic Chemistry 1. Give me a thumbs up if you follow me. If you have a question, feel free to unmute your mic or type it into the chat, and I'd be happy to address that question. Does everybody follow me on this? Or if you don't, let me know. Okay, thanks, Skylar, and thanks, Shelby. Well, let's move on from there. And let's take a look at question 11.2, which again deals with one-step syntheses. And the question reads, identify reagents that would be used to accomplish each of the following transformations. If you're having trouble, these reagents appear in the review of reactions at the end of chapter 9, but try to do it yourself first. So chapter 9 is where we covered the chemistry of alkynes. Okay, so this is alkyne chemistry. Everything on here has to do with an alkyne, right? We're starting with this little molecule here. That's called propyne. And then we're doing all of these cool transformations. So let's start, where should we start? Let's start with the one that's straight up, right? Straight up like Paula Abdul, right? Straight up. Let's see here. If we want to take propyne and we want to convert it to this vinyl bromide, could anybody tell me how I might do that? What kind of reagents I might use? Oh, I just want to add HBr. Exactly, Skylar. I would use HBr, and I would be sure to point out that it's one equivalent, right? Because if I use two equivalents of HBr, I'd end up making this molecule, wouldn't I? Or if I used excess. So here, we're going to put HBr again, right? Because we're simply adding another equivalent of HBr in the Markovnikov fashion. So this is Markovnikov addition of HBr across the triple bond. Now, I have a reaction for you that's really, really important. This is one that comes up all the time with alkynes. If we had this geminal dibromide here, how would I take that and convert it back to an alkyne? Well, the way that we do that is by doing a double E2, right? We do a double elimination, and then we do a deprotonation to make an alkynide. And then after that, we do a second step, which is to treat it with water to do the protonation of the alkynide and restore the terminal or the proton to make a terminal alkyne. So we would put step 1 would be excess sodium amide, NaNH2, and step 2 is water. That's a really important reaction in terms of alkyne chemistry. That's one of those reactions that comes up quite a bit in organic chemistry too. Well, the same thing applies here, right? These two bromines are geminal, right? We call this geminal because they're on the same carbon. If they're on adjacent carbons, we call them vicinal. So geminal and vicinal, you need to know the difference between those two words. And if we have a vicinal dibromide, like we do here, we would do the same thing, excess sodium amide followed by treatment with water to produce the alkyne. All right, let's keep going. Why don't we go in a counterclockwise fashion this time, maybe? I don't know, keep things interesting. All right, let's move on from there. And what if we wanted to take propyne and we wanted to convert it into this carboxylic acid and carbon dioxide? Could anybody tell me what kind of conditions we would do for that? My students came up with a good answer for a similar type process. Yeah, you're in the right vein, Skylar, absolutely. Yes, this is an ozonolysis reaction. Ozonolysis of an alkyne. And in ozonolysis of an alkyne, the first step, yes, is ozone. However, the second step is not DMS. Okay, not DMS. The second step with an alkyne is just to treat it with water. So it's a little bit of a nuance there. And what you do is you end up clipping, right? You end up cutting the molecule right here to make a carboxylic acid. And when you have a terminal alkyne like this one, you end up with carbon dioxide as well. Okay, there we go. Next one is we want to take the propyne molecule and we just want to brominate the heck out of it, so to speak. So we're adding 4 bromine. So for this one, you would just use excess bromine in order to do that. If you only wanted to add 1 equivalent of bromine, well, you would just write bromine and you would be sure to write out 1 equivalent because that's all you need to make this dibromo compound. Okay, I have another question for my students. What if I wanted to take 1 propyne? I can find my slide. Oh, I lost everything. Shoot. While you're thinking about it, I will jot everything back in here again, I guess. So. Okay, so here's the question for my students. What if I wanted to take propyne and I want to convert it into 2-butyne? So I'm actually changing the carbon skeleton here. I'm going from a compound that has 3 carbons to a compound that has 4 carbons. Could anybody give me an idea about what the first step might be here? The first step to go from 3 carbons to 4 carbons. Yeah, thanks, Courtney, and thanks, Skylar. Absolutely. Yes, you're both correct. So I would take that terminal alkyne. In the first step, I would deprotonate it by treating it with sodium amide. And then in the second step, I would treat it with methyl iodide because I'm only adding a methyl group to the end, like that. Okay, I'm going to cover these reactions on the side a little quicker because these are covered in detail in Organic Chemistry 1. But if I want to reduce the alkyne to a transalkene, I'm going to treat that with sodium and liquid ammonia. If I want to completely reduce it to an alkane, I would just treat it with hydrogen and palladium, platinum, or nickel. And if I want to convert it to a cis alkene, I would treat it with hydrogen and a poison catalyst like Lindlar's catalyst. Okay, again, those reactions, these two, this one and this one, are covered in chapter 8 in our textbook. All right, we got 2 more reactions here. The first one, I'll highlight it in blue, or highlight the reaction arrow in blue, is the result of an anti-Markovnikov addition of water. Because if we add water in an anti-Markovnikov fashion across that triple bond, we would end up with an enol that looks like this, which would undergo tautomerization to produce this aldehyde. Well, what are the conditions we would use to do that anti-Markovnikov addition of water across that triple bond? In the first step, we would use 9-BBN or some kind of hindered borane. And then in the second step, just like hydroboration oxidation that we looked at in the last slide, we'd use hydrogen peroxide and sodium hydroxide. And lastly, if I want to take my alkyne and I want to add water in a Markovnikov fashion to produce this enol, which will also undergo tautomerization to produce the methyl ketone, to do that, I would use sulfuric acid and mercuric sulfate. So I'll put mercuric sulfate, sulfuric acid, and water. You need to have all of these reactions committed to memory in order to master the content in Organic Chemistry 2. There is no way no shortcut you can take to memorizing these. At least I wouldn't say there is. They're just very important for my students to know. Give me a thumbs up if you follow me on these reactions. And if you have a question about them, feel free to stop me. Are there any questions about these first 2 problems or reaction that you have a specific question about? All right, good. So it seems like it's pretty fresh in a lot of people's minds. Well, that would be a good thing. That makes me happy. All right. Thanks, Shelby. Good. All right. Well, let's move on and talk about how we would move a functional group around a molecule. These little two-step synthesis strategies that we looked at in Organic Chemistry 1, or you would have covered in Organic Chemistry 1, things like moving a functional group around a molecule. Now, a bromine, I don't know if I would really call that a functional group. It's a halogen, and we can use halogens effectively in SN1 and SN2 reactions to make good electrophiles. So let's say I wanted to do an elimination to produce the Zaitsev alkene. Well, how would I do that? I would treat that with a non-hindered base like sodium ethoxide. Sodium ethoxide. Why would I do that? Because there's two types of beta protons here, aren't there? There's this type that I have highlighted in blue, and then there's this type that I have highlighted in red, or sorry, in green rather. If I use the type or use the one highlighted in green, that's the one that's going to react with a non-hindered base to do my E2 reaction and make the Zaitsev alkene. Then if I want to add HBr in a Markovnikov fashion, I would just use plain old HBr to do that. All right, I'm going to get the rich becoming richer. I'm going to produce this carbocationic intermediates, which is going to look like this. And then bromide is going to come in and act as a nucleophile. Sorry, I'm kind of scribbling here, but you get the idea. And there we go. So you need to know Markovnikov addition. You need to know eliminations and things like that. We see a nice summary of what we did on the last slide with these two red circles. And you can see other ways that we could manipulate the molecule to move the bromine around it. What if I wanted to add the bromine over here? Well, in that case, I would have to do an elimination to produce the Hoffman alkene. Hoffman, right? And the reason why that would produce the Hoffman alkene is because potassium T-butoxide is a big bulky base, right? It's not going to pluck off the most hindered hydrogen. It's going to pluck off the low-hanging fruit to do this E2 reaction and produce the Hoffman alkene. Then I could do an anti-Markovnikov addition to install that bromine. What else? What if we want to move a hydroxyl around a ring? A little trickier, isn't it? Because hydroxyl is not a good leaving group, right? If I want to take that hydroxyl group and I want to make the most substituted alkene, well, how would I do that exactly? Well, first I would convert it to a good leaving group, right? Using tosyl chloride and pyridine, right? This is conversion of hydroxyl into a good leaving group. So toluene, sulfonyl chloride, and pyridine. Then I could do my elimination to produce the Zaitsev alkene. I could do a hydration, right? This is just a Markovnikov addition of water to produce this tertiary alcohol shown here. I could take this alkene, the Zaitsev alkene, I could reform my starting material by doing an anti-Markovnikov addition of water. What else? If I want to produce the Hoffman alkene, I use the same first step in that I convert the hydroxyl to a good leaving group, but then I would abstract this proton using potassium T-butoxide, right? It's a hindered base, okay, like that. That's sort of an abridged mechanism because my hydroxyl wasn't a good leaving group, but you get the idea. What else? Here's a reaction that didn't show up on those first two questions, and that is a Markovnikov addition of water across a double bond that doesn't involve or avoids a carbocation rearrangement. Why don't we put that here? We'll put avoid carbocation rearrangement using oxymercuration, demercuration. There we go. What else? What if we want to move that pi bond around? Well, we already talked about that. If we wanted to move the pi bond around, first reaction here would be a Markovnikov addition of HBr. Why? Because the rich would get richer, right? You have this carbon that has the red hydrogen. Then if you added HBr to it, then you'd have the blue proton and the red proton, and you'd end up adding the bromine. Then you could treat that with a hindered base, like potassium T-butoxide, to produce the Hoffman alkene. So all just using those reactions that we saw in those first two problems to affect these types of desired transformations, which are going to be really important in organic chemistry too. We're going to see a lot of little one-step syntheses over and over and over, and we're going to learn a lot of new reactions in this class. All right, there we go. What else? What if we wanted to convert a double bond to a single bond or a triple bond? Well, if we want to convert a double to a single bond, that way we just hydrogenate it, right? If we want to convert an alkane into an alkene, something with a functional group, what would we do first? First, we would brominate it. Then we would do an elimination. If we want to convert a triple to a double, that's an interesting one. You can either selectively reduce it using Lindlar's catalyst and hydrogen, or sodium metal in liquid ammonia. Or if you wanted to convert the alkene to an alkyne, first you would brominate it, then you do a double elimination followed by protonation. Right? All very important reactions for you to know in organic chemistry too. Well, with that in mind, let's take a look at some practice problems. I encourage you that if you took Organic Chemistry 1 with me, to not look at your old notes or not look at the solutions manual, to see if you can do these questions on your own, because it might be a knee-jerk reaction to say, hey, I remember all those reactions that we learned in Organic Chemistry 1, but when you're just staring at a blank sheet like this, they can get a little trickier. So I'm going to give you a few seconds to think about this one. I'm going to give you 2 minutes to take a look at this problem and see if you can come up with some solutions. All right, let's take a look at the first one. We're taking an alkene and we want to convert it to an alkyne. There's no changes to the carbon skeleton. We're starting with the same number of carbons that we're ending up with, but we want to convert this alkene to an alkyne. Well, the only way that we know how to make an alkyne would be to have this molecule, right? Would be to have this guy, this vicinal dibromide, which we could take and treat with excess sodium amide followed by water. So then the question becomes, how do we get from the alkene to the vicinal dibromide? Well, let's take a look. What we would do, so let me get some of this stuff erased here. What we would do is we would first treat this with bromine. Then we would do the double elimination with excess sodium amide. And then in the last step, we would treat that with water to restore the terminal alkyne like that. All right, let's take a look at the next one. I'm starting with a primary alkyl halide, and I want to end up with a tertiary alkyl halide. So I like to think of this one in terms of retrosynthesis as well. If I could make this compound, methylene cyclohexene, this guy right here, all I would have to do is a Markovnikov addition of HBr across that double bond, and I end up with the tertiary alkyl bromide. So the question then becomes, how do I get from here, from my primary alkyl halide, to eliminating so that I produce, I want to eliminate this beta proton? Well, the answer is I would treat it with either potassium T-butoxide or DBU. And the reason why I would do that is because I want to mitigate or avoid SN2 from occurring. So the first step, let's say we treat it with DBU, because remember, when you have DBU, it is a strong base and weak nucleophile. We have a tertiary alkyl halide, and so we're only going to get E2. And then we produce the methylene cyclohexene, and then in the second step, we would treat that with HBr. Let's take a look at this next one where we move the double bond around the molecule. We're starting with this exocyclic alkene, and then we're making this endocyclic alkene, so where the double bond is inside the ring. Well, if I were to take the exocyclic alkene, so let me just write it out here. If I was to start with this molecule, my starting material, if I treat this with HBr, what's that going to do? It's going to do a Markovnikov addition of bromine across that double bond, and I'm going to end up with this compound, 1-bromo, 1-methyl cyclopentane. So if I want to do the elimination to make the more substituted alkene, the Zaitsev alkene, I would have to remove the proton that I have highlighted in green as opposed to the beta proton that I have highlighted in red. Well, how am I going to do that? I would use a non-hindered base like sodium ethoxide to do that, and I end up with the Zaitsev alkene. All right, last one. Could anybody tell me what the first step in D would be? The first step, what it would have to be. And it's not a trick. Exactly. Thanks, Skylar. The first step has to be bromine and light or bromine and heat. Why? Because when I take methyl cyclopentane and I treat it with bromine, and I'll use light like Skylar suggested, I'm going to end up with this molecule where I have bromine here. And then if I want to eliminate that to make the Zaitsev alkene, well, I'm going to treat it with sodium ethoxide, just like we did in the last problem. And I end up making this compound, 1-methyl cyclopentane. There we go. Give me a thumbs up if you follow me on those transformations, or if you have any questions about those, let me know. Any questions about those? All right, good. All right, well, let's move on from there. So making changes to the carbon skeleton, sometimes you have to add or remove carbons. Not always, but sometimes you do. When you have to alter a carbon skeleton, when you don't have a choice, you got to remember that up to this point in organic chemistry, you haven't learned that many reactions wherein you can manipulate or alter a carbon skeleton. Say, for example, you want to add carbons, right? If you want to go from a 4 or 3 carbon molecule and you want to make a 7 carbon molecule, right now, this is the only reaction we have that you can use to add carbons. You start with an alkynide and you do an SN2 on an alkyl halide or a tosylate maybe, and that way you can expand the carbon skeleton. So we go from 4 or 3 carbons all the way to a 7 carbon molecule. If you want to decrease the number of carbons in the molecule, really the only thing we've got on our plate is ozonolysis. This is ozonolysis of an alkene. Remember, the second step is DMS. When you do the ozonolysis of an alkyne, the second step is to treat it with water. Well, with all that in mind, let's take a look at another practice problem. We have 2 where we increase the number of carbons in the carbon skeleton. In this first one, I'm taking acetylene. That's the name of this molecule, acetylene. And I want to treat this, or I want to convert it into 2-pentyne. So this is 1, 2, 3, 4, 5. This is 2-pentyne. Well, remember that when we take the acetylene and we treat it with sodium amide, we deprotonate it so that we make acetylide. Okay, now technically it's sodium acetylide. Sometimes we like to leave spectator ions out in organic chemistry, so I'm going to do that. Now on one side we have a methyl group. Pencil that in. Over here we have a methyl group, and over here we have an ethyl group. I'm going to add the methyl group first just for fun, and it doesn't matter which order you add these in. And so for that I would use methyl iodide or iodomethane. That's going to do an SN2 reaction to make propyne. So now I've got propyne. I'm just going to move it over here a little bit. Okay, but I have another acidic proton, don't I? I have this proton, which has a pK of about 25. So I can deprotonate that one using sodium amide. I end up with the propanide like this, and then I just treat that with ethyl iodide. So I'll write it out like this. This does another SN2 reaction like that, and I end up with my desired product. So I have a methyl group over here, and I have an ethyl group over here like this. If we tally up all the steps, there's a total of 4 steps. The first step was sodium amide. The second step was methyl iodide. The third step was another equivalent of sodium amide. And the fourth step was ethyl iodide. The next question is in a similar vein. We're starting out with a molecule that has a total of 7 carbons, and 6, 7, 8, 9. We want to end up with a molecule with 9 carbons. I'll just show you the answer to this one pretty quickly. You can assume that you have small molecules or small ions like sodium acetylide. Okay, like this. All you'd have to do is treat the molecule with that. So if you treat this with sodium acetylide, I'll write it out here, right? That would do an SN2 reaction on benzyl bromide like that, and you end up with a compound that has 9 carbons like so. And thus, one of the first questions you want to ask yourself when you're dealing with a synthesis problem is, is there a change to the carbon skeleton? If there is, is it gaining carbons? Is it losing carbons? Decide what to do. Is there a change in the functional group, identity, or its placement? You have to decide what to do there. And the best way to master this kind of content is to do what? Many, many examples is the only good way to do this. Let's say you had a problem like this, where we have a compound that has 5 carbons to start, and we end up with a compound that's got 7 carbons. So we're tacking on this CH2, CH3, or this ethyl group kind of at the end like that. We've got a terminal alkyne, so what are we going to do? We're going to first deprotonate that using sodium amide. Then we would use ethyl iodide, and then we would do a reduction so that we end up with the trans-alkene. How do you do that? You treat it with sodium metal and liquid ammonia. So the first step would be sodium amide. The second step would be ethyl iodide. And the third step would be a reduction to form the trans-alkene, so sodium and liquid ammonia. So that's kind of my quick treatment for, a problem that they take a few slides to solve here. And here's the overall reaction scheme right here, a 3-step problem. So with that in mind, I want to take a break and let my students think about these 3 problems here. And then we're going to come back and we're going to tackle these 3 problems, which all involve changes to the carbon skeleton.